Welcome to this session about big data with Python. We will look at the different file formats to see which one could be more effective. Also how to allocate resources sufficient to data size. And also using a technique called data chunking if the memory is not enough. And also having grasped the surface on more efficient packages. Yes. So what is high performance data analytics, HPDA shortened? Well, you see the description here. A subset of high performance computing which focuses on working with large data. And big data then refers to data sets that are too large or complex to be dealt with traditional data processing application software, or the size of your RAM, or random access memory. Yes. So what do we need to cover? Well, file formats and methods to deal with the data, like the chunking and RAM allocation, as said. So, types of scientific data. And now we speak about the file formats and to some extent also the variables inside Python. So what do we need? We need the data to be, well, maybe not always. So we have some questions. So do we need the data to be human readable? Sometimes it's good to look at the data itself in the files, and then it could be in text format so that we can see the numbers or the text. But on the other hand, maybe we want it to be space efficient, and how to do that? Well, it could be instead of text format, it could be in binary format, so just the zeros and ones, and that may reduce our space. There are other things one can think about here. Tidy data or arbitrary data. Tidy, that would be that it is easy to overview. Maybe it's the same format everywhere. Whereas arbitrary could be like one section of the file is a table, another one is metadata, that is a description of the data. Yes. Or is it array data? So is it gridded? Is it in some kind of matrix form and such? And do you want to share the data or should it be for long-term storage? So, yeah. So with this in mind, we can go further and look just at the basic, just briefly. So everything is bits and bytes, and you may know about the building blocks here. And we can have a numerical data with different data types. So this could be within Python that you choose to work with variables, maybe with integers, and it could be short or int, or floating point, single or double. So for some cases, the precision is not that important. So maybe 1% error or so is sufficient. Then you can store it in a single format. And yes, that will make your program faster and you will have less data storage if you save data, or you will occupy less part of, a smaller part of your memory. Then we have text data. Not so much to say about this. A bit more can be said if you're interested. All right. So that's the basic or the smallest part. But now one can decide on how to store your data. So data in scientific applications could be more complex and structured. So it could contain both numerical and text data. And then you can, of course, choose to have one file for the text or several files and several other files with just the numericals. But then you may need to read into your program several files and then combine the output there to get a full understanding of whole your data set. So what is what? Like, so the text file maybe describe what is in one of the columns of another file. So yeah. So it could be a bit complex. So you can have a tabular data where we have like rows and columns. So for instance, CSV files. A variation of this is grid data, which could be in earth science or atmospheric science or astronomy. If you want to mimic the nature in the 3D, mimic the 3D structure of the nature, some kind. So that is gridded. So that means it could be three-dimensional even, and how to work with this. Yes, and if you're more interested, you can look at this. So it could be in format called HDF5 or CDF. These are common file formats for this 3D data, or even 4D data if you include the time as a dimension as well. Metadata, that's about information about the data. Yes, there might be different conventions, and for environmental science, NetCDF files are quite common, for instance. And you may know all of this if you are already in natural science, for instance, or environmental science, I would say. CSV I mentioned, and here, yes, this is about the HF5 and SCDF. So if you're interested, you can go here and follow some links maybe as well, or just see. Of course, you can search for this on the internet, but it also tells you about how good it is in different circumstances, basically. So for instance, NetCDF, what we can see that it is in binary format, that you can use, for instance, X array to read it. To some extent, pandas could be enough, but not always. And space efficiency is good, and it's good also for archiving or sharing. The thing here is also that it has a standardized structure, the metadata. So you have the metadata inside the NetCDF. I can also say that with the NetCDF is that when you read NetCDF data into, for instance, Python, you can choose to just read some variables. So you can, for instance, extract only temperatures maybe, and or just all data for one time step. So you don't have to load everything from the file into your memory directly. So that means that you can files being maybe hundreds of gigabytes big, and then still be able to load into Python smaller parts. So here we have an overview of where, like if it's human readable, these check marks will show that it's in text format, so you can read it directly. But for instance, CSV is not very space efficient, and it doesn't work for arbitrary data because it's tabular or gridded. So it's more for what you call tidy data. Array data, I thought it would be that, but maybe if it's more like three-dimensional, I would say. So HF5 and CDF is good for this. Yes, so if you're interested, you can go further into the details here. This orange mark is that it's okay in some cases to use this. So we see that there is no of these formats that is good in any case, in all cases. For Excel, it's actually just maybe good for tidy data. Yeah, and so on, so forth. And if you're more interested, we have some courses like this ENCCS course, and also a course given by Aalto Scientific Computing, Python for scientific computing, yes. And for instance, we have some information about the X-array package that I will cover just in a few minutes. Yes, so this is about the data files, but now what about the computing efficiency within Python? So since now Python is an interpreted language, and we have many features that make development rapid, we also have a result that the performance is reduced in many cases. For instance, we have dynamic typing and flexible data structures. That means that it's not very efficient because it's not told explicitly how the variables are stored in the memory. So this flexibility reduces the performance. But there are some packages that are more efficient than NumPy and Pandas. So SciPy, for instance, is a library that builds on top of NumPy, which has some parts that are compiled with Fortran or C. And as it is compiled, it will be also much faster. And we also have some more information from the ENCCS course material. I would just like to just briefly mention the X-array package, which is a good tool if you are using multi-dimensional arrays, for instance, in environmental science. So the syntax is a bit borrowed from Pandas, so you may be a bit familiar with this, and also integrates tightly with Dask, which I will talk about in a couple of minutes as well. Especially good to use when you are using NetCDF files. And here are just some functions that makes it work in a good way, an efficient way. Yes. And you can explore these in one of the exercises below. So another thing to think about when you're working with big data is that you can actually allocate more RAM. And what you can think about here is that when you are using your program, you will read files or parts of the file. And while doing the calculations, you may be creating new variables, and that will take more space in the memory as well. So you have to think about what will happen during your program. Will the memory be more occupied by data or not? So maybe you need more RAM than you will get from just using one core on the login node, or if you have allocated one core on a compute node, because you're not using any parallelisms at all. In the coming session, you will hear about parallelisms. But maybe you don't use it, but you need to run serially, but you need lots of RAM. Then you can still allocate several cores, or a full node, or a bigger node, because our systems, the different classes in Sweden, they have some basic compute nodes, but also some with more working memory on. Yes. So what will happen is that the memory will be shared among the cores, and you can also say that one core will actually give one certain amount of memory, depending on how big the node is and how many cores there are. And using more cores will basically linearly increase the amount of memory available. So you can look at this. We have this table of hardware. We look at Kaiser, for instance. We have, or Rackham, might be easier. We have 20 cores on the compute node, and one compute node will have 128 cores in the gigabytes, unless you are booking a fat node with more memory. So in principle, 20 cores will actually share 128 gigabytes. So that means if you just allocate one core, you can divide 128 divided by 20. That will be 6.4 gigabytes. So in principle, in theory, that is, you would get 6.4 gigabytes per core. So yes, and with 5 cores, you take 6.4 times 5, and then you will get 32. And if you want to allocate several cores, if you remember, you put this flag -n. It's quite common. Or if one full node is not enough, you can book one node with more RAM. Yes. But then we have something called Dusk. This is a package for Python. And this can be used if the memory is not enough for your data or for your calculations. So this is how to use more resources than available, basically. And here is also the map showed by Rebecca in the panel session. So if you, for instance, need more than 3 gigabytes of memory, then you will go to this and you can use Dask. While looking at this, we can also see that if it's 2D, we can well, if it's not 2D or 1D, we could try with the X array. So in other cases, use pandas, for instance. Yeah, so 3 gigabyte for Rackham, that would be like yeah, a bit more because we had lots of memory per core. So this would be limited by how much memory you get per core. Because pandas, I think, can only use one core, the memory from it. I might be wrong. But yeah, it depends, I guess. Yes. But typically with big data, Dask is a good choice. So it's popular, and it's the Dask package itself is composed by two parts. We have a cluster part and also the big data collection. So it's called collection, basically. For the first part, maybe we will introduce this in this course in the future, but right now you can read more in the ENCCS course. We will briefly cover a bit more the collections. So it's, for instance, you can work with arrays or data frames or something called Dask bag. So this bag is for Python lists. Data frame is yeah, an extension of Pandas data frame, basically. An array is an extension of NumPy arrays. So, for instance, if you're using a Dask array, it will feel like a NumPy array, but Dask will actually use something called lazy execution. So that basically you build up complex or large calculations symbolically. So you define some kind of recipe for what you want to do. But then the calculations are done when, yes, basically, it's not performed until you actually ask values to become computed. For instance, print mean values. Yes. So Dask divides arrays into small pieces or chunks, as small as necessary to fit into the memory. And then I said operations are delayed. And then when the computation is actually to be performed, data is loaded into memory and computation proceeds in a streaming fashion, block by block. So an example here is where you create a random matrix with 10,000 rows times 10,000 columns. And it will, in this case, it's random numbers. And you also tell Dask that you want chunks in tiles of 1,000 times 1,000. So this will be 1 million cells, but that will be enough for, well, I mean, that will fit into memory, whereas this will probably not, because this will be hundreds, 100 times larger. So you see that we have 10 chunks in each side. So 10 times 10, that's 100. So in this case, we will have 100 different chunks of this big matrix. And then we perform some calculation. And it can also use multiple threads on your machines, on your machines. So you could actually use several cores here. So it will do the calculations in a parallel manner. It could also be distributed to multiple machines. That means across nodes. But if you only run on one core, it will perform the calculation first on one chunk, then the next one, and this will take 100 times compared to one chunk in total here. So 100 times this one. In time, if you instead booked or allocated 10 cores, it will instead run at 10 chunks in parallel, and the resulting time will be about 10 times. Well, it will be 10 times faster, except for some overhead time, because it will also take some time to put everything together, more or less. Yes, but more about this if you go to the course material or to the Dusk homepage. There is also for machine learning a specific package, and you can also have a distributed computing with Dusk. And yeah, more about the distributed will happen tomorrow with or in the parallel session with Pedro. Yes. So then we have the exercises, and there are descriptions in all centers in how to go further with this. Yes. So here are the key points. And with that, yes, and here we have also some more documentation or other courses that you can look at if you are more interested in this. So that's all in this session, and see you another time.